Today we have Jae Lee talking to us about a quantum HG module via Quasimap Invariants.
Thank you. So I'm Jae Lee. So today's talk about a newly defined group cohomology module structure via Quasimap Invariants. And this is joint work with Mark, Shoemaker, and Renzo, Cavalieri, my advisors. So I'm going to start from talking about what is enumerative geometry, and then tools to study enumerative geometry, which is cohomology and moduli spaces. And then I'm going to define a new Quasimap quantum H star G module structure. And then I'm going to give an explicit example of this module structure for Hirzebruch surface of type 2. And then we'll end up with a conjecture. So here is the diagrams for enumerative geometry. So in math physics, there is a string theory that studies strings, which consists of every what is the string? It is in every steps, and then that is, I think, related to a pseudo-holomorphic curve in the symplectic geometry side first, and then people thought that it's gonna be okay for algebraic geometry to work in a setting in algebraic geometry. And then what they do is counting such a curves, which is like strings. And then it boils down to combinatorics. And then everything inside, we have a enumerative geometry. So what is enumerative geometry is the study to count geometric object subject to geometric conditions. So that's enumerative geometry. So now here's basic enumerative geometry question. First thing, how many points in the intersection of these two lines is basically, you can see that there is obvious one, which is 1. And then how many lines passing through these 2 points? It's going to be 1 as well. Then in this case, how many points in the intersection of these one parabola and then one line? So in the picture, this is not intersection. But once we work over C, complex numbers, they're going to intersect at 2 points. So we're going to work over C. Now here's 2 parallel lines. They are not meeting right now. But that's the situation that we want to avoid. So we're going to deal with the projective varieties. So in this case, if we introduce point at infinity, these 2 parallel lines are going to be meet at the infinity point. So that's kind of a very basic enumerative geometry questions. Here are more questions for in enumerative geometry. So it starts from how many lines on smooth cubic surface, lines on general quantic threefold, conics tangent to 5 plane conics in general position, irrational plane curves of degree d passing through 3d minus 1 points. So these all 4 questions are having specific stories. So first one, so lines on a smooth cubic surface. So this is related to Schubert calculus, the study of cohomology ring of Grassmannian. Then the second question, lines on a quintic threefold. Quintic threefold is an object that we can see from string theory or math physics. And then this question is very related to math physics. So the enumerative geometry is not just a mathematical curiosity. Beyond that, it is related to other subjects, especially like math physics. And then this 3264 is known as a title of a book Now here you can see a tangency condition. And then that's exactly a geometric condition. Then the fourth one is the rational plane curves of the UV. The number of these plane curves is counted by Hirzebruch using his recursion relation. So these are very famous questions in enumerative geometry that you can see it from the start. So now I'm going to introduce tools to study enumerative geometry. So first thing is cohomology. For a space X, we have an algebraic object which is called cohomology ring. And roughly what the cohomology ring says is that an element of the cohomology ring is a subvarieties with some equivalence relation. Now this is a ring, so it has addition and then multiplication. The addition is roughly is taking just union, and then multiplication is taking intersection. And then especially identity for this multiplication is the fundamental class, because you take the intersection with this fundamental class, and then it's just you're gonna have a V. So that's the cohomology ring. So for example, the cohomology ring of a projective plane, so the projective plane is the set of all lines in C3 passing through the origin. The cohomology ring of this projective plane is univariate polynomial ring, quotient by relation h cube is equal to 0. So basically, if you pick a general polynomial here, it'll be represented by degree 2 polynomials, and then especially monomials of degree 0, which is 1. This represents the class of, which is the fundamental class. It's class of a whole variety. And then H represents the hyperplane class. In this case, hyperplane is just a line. So H represents a line. And then H square, you take the intersection of two lines, and generically you're going to get a point. So H square represents the point class. So that's the basically a cohomology ring of the projective plane. So what the cohomology ring says is the information of how subvarieties are intersecting one another. Yeah.
So if addition corresponds to taking a union,
Yeah.
what is the polynomial like h squared plus 1?
H squared plus 1.
Because then you're taking a union with all of P2, right?
H squared plus 1. Yeah, that's I think.
Is it equal to 1 if you do that? Or is it
No,
something
it's
different?
not. So there are certain technicality when I transfer into intuition from the abstract reverse definition. So there are 1 plus h squared, I guess. You can just think that as counting one whole space and then just 1 point. Yeah. Any other questions? Okay. So second tool is the moduli space. Moduli space is a space that parameterize geometry objects of a certain type. So in my talk, our interest is exactly morphisms from P1 to a projective variety X for fixed degree beta. And then we're going to think that there is no common factors, so that it becomes a actual map of degree beta, then that becomes a smooth rational curves of degree beta in X. But the thing is this, if I collect these objects, the problem is they are not compact. So in fact, moduli space is defined to parameterize actually a family of geometric objects. If I think families, especially this for example, this family over a line, and then each fiber has each fiber is a smooth rational curves of degree 2. So generic fiber gives you degree 2 curves. But once you deform to the central fiber, this becomes a normal curve. Then this normal curve is not in here. So that's why this is basically not compact. So we're going to compactify this space by putting such a degenerations. Then there are two ways to do that. So one is a moduli space of stable maps. Then the second one is moduli space of Quasimaps. So the stable maps, I'm going to put an infinity symbol for it, and then 0 plus symbol for the Quasimap moduli space. And then I'm going to put some of the markings on my source curve. Then that'll play a role in a second, in a minute. And then when we compactify, there are certain technical conditions, which is called stability conditions, related to a low canonical bundle. But the stability condition basically says that in the stable map case, we do have a rational tails. And then for the Quasimap case, stability condition allows us to have a base points.
What's a base point?
So I'll tell through the
Okay.
from the example. Yeah. So so here is an example of a degenerated map. Because I have a nodal curve. Then there are 2 points. Then I'm thinking of a degree 3, and then my target space is projected plane. So this blue component, it has a degree 2, and then this one has a degree 1. So this goes to a line, and then this blue line goes to a conic. So that's a valid map, which can be realized as a stable map and Quasimap. But this map, this brown component doesn't have any marking. So this kind of component is called a rational tail. And then this is an example of a stable map, which is not Quasimap. And then this is an example of a Quasimap. So in fact, a Quasimap parameterizes not the maps, but the sections. And then in this case, sections can have a common factor. And then when we have a common factor of sections, we do have points where the map is not defined, like a rational map. So here, this, and then that is called a base point. So here, this represents the base point. So this brown part has a degree 1, and then because the degree 1, there is a base point of degree 1, so this collapses to a point. So we don't have a line in the image. Then this is a example of a Quasimap, which is not a stable map. So any questions for what is stable maps and fuzzy maps. So that's two compactifications of maps from P1 to target. So now, because we added some markings on the source curves. Then here is the role of that markings. Because we have a markings, and then an element in our moduli space is a map. And then here I put epsilon, and then epsilon can be an infinity that represents a stable map. And then when epsilon is 0 plus, it represents a quasi map. So if I have an element in here, I can plug in ith marking to the map, and then that lands on my target space. So that's an evaluation map. And then for the quasi-map case, because we have a base point, but in the definition of a quasi-map, it says that base point must be distinct from markings. So for the quasi-map case, this evaluation map also well-defined. Then this evaluation map induces a full-bank map, which can be regarded as just taking pre-image. And then this map is from cohomology of space X to cohomology of our moduli space. And then if I take a class in the cohomology of X, and then think about the evaluation map at that class, this class in the target cohomology represent the class of stable or quasi maps whose image curve pass through the subvariables, through the subvariable that I chose from the first. And now, using this evaluation map, I can define GW invariant, which is from stable maps, and then Quasimap invariant, which is from Quasimap moduli space. And then this is defined by taking integral over my moduli space of the product of evaluation maps. If I do product here, this class of the product represent stable or quasi-maps whose image pass through all the gamma I from all the gamma i's from 1 through n. And then here integral basically counts the number of the points in the intersection. And here I put virtual for this one. So when we think about the moduli space, we have to integral over a fundamental class, but in this case, that's not well defined. So we have to use some machinery to define some virtual fundamental class to define this integral. The one example of this invariant, when epsilon is infinity, which is a GW invariant, and X is projected plane, I can take degree beta to be D, and then put 3D minus 1 markings. And then choose 3D minus 1 point classes. And then this GW invariant represent the number of rational plane curves of degree D passing through general 3D minus 1 points. Then that is computed from the Mumford's renowned formula. Any questions for defining invariants for this one. So those were the kind of tools that tools to study enumerative geometry. Right now, we're gonna put something for my work. So let's say V is finite dimensional C vector space. Then there is a reductive group is acting on the space, a vector space V. And in this case, I can take the GI quotient after choosing a character of G. So that's this one, and then this will be my target. And then I'll put more markings here, K markings, which is different from M markings. The first is M markings. These are called heavy markings, and then these K markings is called light markings. And what's the difference between heavy and light markings are light markings can collide with other light markings. So in this case, we can also think about the evaluation map at these light markings. And then that's slightly different from evaluation at heavy markings. The thing is, light markings are very similar to base points. In fact, light marking can be viewed as a base point of a map in certain expression. So by taking product with some other space, we can view light markings as base point. And then since these are very similar to base points, when we evaluate at this light marking, we can land on some unstable locus of V. But this object, which is called stack quotient, also has a unstable locus compared to this GIT quotient. So GIT quotient, basically you throw away the unstable locus and then do the quotient. But this space, we do also have information of unstable locus. And then when we take the evaluation map at light markings, they can go to unstable locus. So now let's say M is 2 and then K is 1. So 2 heavy markings and then 1 light marking. Now I can define a 2-bar 1 operation. So take Ti to be a basis for the cohomology of my target, and then Tj for the dual basis. And then for sigma, a class in the cohomology of stack quotient, and then alpha, a class in the cohomology of target space. We can define 2-bar 1 operation in the following way. So here is a 2-bar 1 invariant. It's not too different from the invariant that I defined. It just uses a light marking and then this evaluation. And then here is Q for the variable of a deformation. So now sigma is from the cohomology ring of stack quotient, and then alpha is from the cohomology ring of the target space. So it seems like this cohomology ring is acting on this cohomology ring. But when we have an action of this one to this space, we need to check some compatibility condition. So the theorem that we proved is that the action that we defined, that the 2-bar 1 operation that we defined, is going to be compatible with the product in this cohomology ring of a stack quotient. So basically when you act to alpha by tau first and then sigma, that's gonna be the same as acting on alpha by the multiplication of sigma by tau. And then it seems like a associativity in the sense that here is a parenthesis and then here is a parenthesis. So we do this for the Quasimap 2x1 invariants, but if we do this one with the three-pointed GW invariant, and this equation is called the WDVV equation, which is related to associativity of the star operation. And then a key idea for the proof of this one is that if you fully expand this equation, the left-hand side and the right-hand side, in the GW invariant case, there's going to be a 4 markings that, so if you forget all the structure except the pointed source curve, so that's going to be land on here, the m bar 04. But in our case, we're going to land on m bar 02 bar 2, which is the lowest common space. And then these two spaces are isomorphic to P1, and then we can use the fact that all the points induces the same class in P1. So we use that fact to prove this one. So okay, we defined a well-defined new module structure on this one. So I computed explicit module structure, especially for Hirzebruch surface of type 2. So Hirzebruch surface is known as a P1 bundle over P1. In this case, there's a twist by 2. But Hirzebruch surface can be also realized as a smooth toric surface. As a toric variety, it has a fan, which is a combinatorial data. Then this is the fan of Hirzebruch surface of type 2. So here is the rays, and then there is also cells in between two consecutive rays here. The cohomology of a Hirzebruch surface can be computed using combinatorial data. And then this is a representation of the cohomology. I picked D2 and D4 because this kind of matches with well with in my computation, with something in my computation. And then this smooth toric variety has a quotient description from the C to the number of the rays, which is C4 in this case. And then quotient by a two-dimensional torus. And then here 2 comes from the rank of the Picard group. And then this is the corresponding state quotient of the Hirzebruch surface. With the with action defined through this matrix. This action is this two-dimensional torus acting on, tells us this two-dimensional torus acting on this four-dimensional space. And then we need to know cohomology ring of the stack quotient, and then this is exactly the same as the so here C to the 4 deformation retract to a point. So this is this can be realized as the point mod of this two-dimensional torus, and then the cohomology of that is the cohomology of a classifying space or group cohomology of the two-dimensional torus. And then that is exactly the two variables polynomial ring. So here, this two-variable polynomial ring is acting on this cohomology through the 2x1 operation that I defined. So any questions so far? So here's the description of the group cohomology of two-dimensional torus module structure of on the cohomology ring of Hirzebruch surface. So this one, these are enough to know every module structure. And this computation requires some time to finish. And here, this f of this function f is defined in this way. And then here, there is a central binomial coefficient, and that is related to some invariant. Then I'll tell a little bit more about my computation for this list of structure. So recall the 2x1 star operation. So this is defined in this way, and to know this operation, we do have to know all of this type of 2x1 invariant, Quasimap invariant. And then here, this sigma is from the two variable polynomial, but this has a linearity. We can say that this is a monomial of degree, some degree. And then using the compatibility equation that we proved, we can reduce the degree of this one to be just so this is like x to the alpha, y to the beta, and then we can reduce to x and beta using this compatibility condition, because this can be like a x times y that is the same as the y is acting on here and then acting on x, so we can reduce this to be a degree 1 monomial. And we introduce the light points, which is this part. And then when this has a degree 1, because so in this case, from introducing light points, we do have a divisor equation. Basically, this divisor equation is, you can take this degree 1 monomial part outside of the invariant by multiplying this beta, so that this divisor equation, this 2x1 invariant boils down to a two-pointed invariant. Now this two-pointed invariant can be computed using Batyrev localization. So that's kind of steps, and then this also Batyrev localization computation also requires some amount of work. And any questions for the computation? So that's the computation technique. So that theorem of this compatibility equation, and then computing full description of a module structure for cohomology of Hirzebruch surface is my work. And then what represents my work? What my work represents is I'm gonna tell right now. So let's think about the quantum cohomology ring. So quantum cohomology ring is an algebraic object from a smooth projective variety. this is kind of a ring, has a product, then that product is a deformation of the product of usual cohomology ring. So somehow you can recover from product in here. You can recover the usual product in here from the product on here. So let's see an example. Quantum cohomology of P2 is given by C bracket H divided by the relation H cube is equal to Q. So in the usual cohomology, the product tells us the information of the intersection. But what does this quantum product tells us? So let's think about this HQ. HQ is H times H squared. And then H was a line, H was representing line, and then H squared was representing point. And then generically, a point and a line in the projective plane will not going to meet. But what does the quantum product tells us is it's the information how this point and this line are connected. Not the intersection, but how they are connected. That's the information, what the quantum product tells us. And then in this case, they are related by a line. And then that line can sweep here so that it forms like a plane. And the plane is a fundamental class in this case, so which is 1. That is encoded as the coefficient of Q. So that's the quantum product, which is defined through a 3-pointed WDVV invariant. And then this quantum cohomology is important in the sense that in math physics, this is kind of related to string theory and mirror symmetry. But the problem is this is kind of difficult to compute.
Sorry, Jay, could you explain again how you got Q, what the geometric intuition was for why H cubed is equal to 1Q?
So if I have a two lines in general, they are going to meet. So which means we do have a point of intersection. So the usual product tells us that information of intersection. But the quantum product tells you how two subpolarities are connected through some curves. How they are connected. They are not going to meet in general. So point and line will not going to meet. But they are connected through a line here, right? So the information, how they are connected through some curves, is encoded through
So the line is saying that is that the 1 in the coefficient or the exponent of the Q?
So here it can be connected through a line, but it's not just a line. There are plenty of lines here, which form a plane. The plane, the class of a plane is 1 in this case.
I see.
That is included as a coefficient of Q.
So the plane is the 1, because all the lines connecting that black point and that black line sweep out a whole plane. And the exponent of Q is 1, because those lines are degree 1 curves.
So actually, there is a
wow.
so triangle shape there, but it seems it's not appearing.
Right, I know what one is. What's Q? What does Q represent?
Q is just a variable for deformation.
Gotcha.
But the power on Q is the degree of the curves connecting those two.
Yeah, exactly. But the problem is this is difficult to compute in general. So now, in 1993, Batyrev defined a ring for a smooth projective toric variety. So the definition of that ring is this one. So here, the polynomial ring, then the number of variable is the same as the number of the rays in the fan. Then there are two types of a relation. The first relation tells you how rays are related to each other. And then this relation is called quantum Stanley-Ariza ideal. The nice thing here is that this algebraic ring, is fully defined through combinatorial data of a fan. So we can compute this relations from that data. Because this is defined through purely algebraic way, what would be the geometric interpretation of this Batyrev ring? When my space, smooth projective toric variety, is Fano, which means anti-canonical bundle is ample. Equivalently, if you multiply anti-canonical divisor to all the effective curves, you're gonna get positive number. So it's related to a strict inequality. In this case, Batyrev ring is the same as the quantum cohomology. So it's pretty difficult to compute. The quantum cohomology is pretty difficult to compute through a geometry, but it can be computed through a complete algebraic, complete combinatorial way. But if we weaken this Fano condition, which is called semi-positive. So I said Fano condition is related to a strict equality. We can weaken that condition to be like to replaced by weak inequality. So that's called semi-positive condition. So more precisely, anti-canonical bundle is numerically effective. And then in this case, this equality does not hold. And then that is shown from the example of Hirzebruch surface of type 2. But we computed a full description of a newly defined module structure. And then this Batyrev ring has a natural module structure just by thinking of this polynomial ring is acting on this ring. Now here is the Batyrev ring of the Hirzebruch surface of type 2. It has a relations, these two relations. And then from the computation of all the module structure, we can compute and then have two relations. And then here sigma 2 star 1 that can be viewed as x2 here. So acting on this one by sigma 2 is multiplying x2, so this can be realized as a x2 square. And then here this can be viewed as a x4 square times q4. So these are so this one is the same as this one, and then this one is the same as this one. So we can see this module structure and then Batyrev quantum module are the same. So we kind of made a conjecture that they are going to be the same in general case. So the quantum H star G module structure on the cohomology of target coincides with the natural module structure of the Batyrev ring of my target when my target is semi-positive. So that's our conjecture, and then that's going to be my future work. And then that's it for today.